In today's Calculus 3 video, we're going to find the local extrema and saddle points using the second derivative test. And in short, we just take the first derivative of x and y and set it equal to 0, which will help us find our critical points. Our next step would be to find the second derivative of each of those, and then a mixed derivative, which is shown over here, of the derivative of x, and then finding the derivative of y after finding the derivative of x, and then squaring it, which is used here to find a discriminant, or also known as the Hussein determinant. And then after finding our double derivatives and our discriminant, we can use these rules over here, where given the information of our discriminant and our double derivative, we can find if it's a local minimum, local maximum, saddle point, or an inconclusive test. Now, if you want a visual representation in 3D, a local minimum just looks like a bowl, a local maximum looks like an upside down bowl, and then a saddle point is just a saddle looking shape with its point in the middle. Now, while we're solving these problems, I will go over this checklist, which isn't too complicated. It just goes over the steps on how to solve a problem when it comes to using the second derivative test. So again, we find our first partial derivatives, set it to 0. We'll find our critical points using methods I'll show. We then find the second partial derivatives. We calculate the discriminant with the formula I gave, and then we use the discriminant and the critical points to see whether we have a minimum, maximum, or a saddle point. Now for our first problem, we are asked to find the local minimum, maximum, and saddle points of the equation f of x of y equals x squared minus 2xy plus 2y squared minus 2x plus 2y. Now I'll just summon our checklist over here, and I won't make it too big. But according to our checklist, our first step is to find the first partial derivatives and then equal it to 0. So let's do just that. Our first partial derivative of x equals 2x minus 2y minus 2. And like the instructions said, set it equal to 0. And the reason for this is to find our critical points. Now notice there's a pattern where we could take out a 2 and leaving inside the parentheses gives us an x minus y minus 1 equal to 0. Now dividing both sides by 2, we get x minus y minus 1 equals 0. So we could take that constant to the other side and we get x minus y equals 1. Now for our first partial derivative of y, we do the same exact thing except taking the derivative of every time we see a y. So we get negative 2x plus 4y plus 2. And don't forget to set it equal to 0. Now again, there's a pattern where we can take out a 2 because they're all factorable by 2. So we get negative x inside the parentheses plus 2y plus 1. And we set it equal to 0. Again, we divide each side by 2 and we get negative x plus 2y plus 1 equals 0. And again, I like moving the constant to the right side, so let's do that. Now if you're wondering how to find our x equals or y equals, we could use the method of substitution where we could set one of the variables equal to something. For example, this side equals to x equals 1 plus y and plug that in for our x here, or we could use elimination. So in this case, I'm going to use elimination because if you add these two together, which I will organize in a row like this, we get x plus negative x, which equals 0, negative y plus 2y, which equals positive y, and 1 plus negative 1, which equals 0, leaving us with y equals 0. Now that we know that our y equals 0, we could find x by just plugging 0 into every y we have. So we could plug it either into our first derivative of x or our first derivative of y, but I'll show you both. So in this case, if y equals 0, we get x minus 0 equals 1, giving us x equals 1. Now to check our answer, we could just do the other side as well, where if y equals 0, we get negative x plus 2 times 0 equals negative 1. Further simplified gets us negative x equals negative 1. And it's the same thing as x equals 1. So now we know with this information that y equals 0 and x equals 1. This is important because that gives us our critical point with our x coordinate being 1 and our y coordinate being 0. So that is our first critical point. In our checklist, which I'll make bigger because I could barely see it, we found the first partial derivatives and set it equal to 0. And we found our xy using either substitution or elimination methods. In this case, it was elimination. Now our next step is to find the second partials of f of xx, f of yy, and a mixed partial of f of xy. Now this step is fairly easy, as all you do is get the original first derivative of each, which I'll bring down each of them down here, and just take the derivative once again. So our second derivative of x is just 2, and our second derivative of y is just 4. Now remember, to find a discriminant, we need the second derivative of x, which we found, multiplied by the second derivative of y, which we also found, minus the mixed derivative of xy squared. Now if you're wondering how to do that, notice that the first variable on the fxy is an x, so you just get this derivative, which we already have, 2x minus 2y, and then find the derivative using the y. So over here, you notice there's only one part that has a y, which is negative 2y, so we just take the derivative of that, and our f of xy equals negative 2. So now we have all three pieces needed, which on our third part of their list we can check out. I like that. And all we do is just plug in. So our discriminant equals f of xx which is 2, f of y, which is 4, and our f of xy, which is negative 2 squared. Simplified, this becomes 8 minus negative 2 squared being 4, and our discriminant becomes 4. So now that we know that we have a critical point at 1, 0, and our discriminant is 4, we're going to look at our rules. Now the rules state if the discriminant is greater than 0, and the second partial derivative of x is also greater than 0, this is a local minimum, and if our discriminant is still bigger than 0, but our second derivative of x is less than 0, that will give us a local maximum. So if you want to remember this easily, just look at the second derivatives and know that the discriminant will always be greater than 0 when looking for a min or a max. Now it's different with the saddle point because it will be fairly obvious when your discriminant is going to be below 0. But if your discriminant does equal 0, that's going to be an inconclusive test and you have to find another way to do it, similar to how we did series in calculus 2. Now notice, our second derivative of x is 2, so our f(x)(x) is greater than 0, since 2 is greater than 0. Our discriminant is 4, which is also greater than 0, so our discriminant is greater than 0. This matches exactly what a local minimum would give us, according to our rules. Now that we know our point is a local minimum, we can conclude that the point 1, 0 is a local minimum since our discriminant equals 4, which is a positive number, and our second x derivative equals 2, which is a positive number. And that is our final answer. So our next problem is going to ask us to find the local min, max, and saddle points of f of x of y equals y cubed minus 3y plus x squared. Now I'll summon our checklist again, but try to remember this list in general. So we're going to find the first partial derivatives and set them to 0. So f of x equals 2x, which again set to 0, immediately giving us our x, which equals 0, and our y equals 3y squared minus 3, which you can see we could take out a 3, giving us y squared minus 1 in the parentheses equals 0, and dividing both sides by 3, we get y squared minus 1 equals 0, y squared equals 1, and finally y equals plus minus 1. So because of this 0, because of the plus minus 1, we have two critical points. Our x stays the same in both points, being 0, 1, and 0, negative 1. We can check off finding our first partial derivative and setting it to 0, and then finding our critical points using substitution or elimination, which I don't even think we had to use. Now our next step is to find the partial derivatives the second time. So bringing down our first derivatives, we just take the derivative of our x again using x, giving us 2, and then we set our first derivative and take its derivative again using y, giving us 6y. And don't forget, we need to find our mixed derivative f of x of y, which is just 0, since our first derivative of x doesn't even have a y, so it's just 0. Now plugging into our formula of our discriminant, which equals the second derivative of x times the second derivative of y minus the mixed derivative of xy squared, we get 2 times 6y minus 0 squared, leaving us with 12y as our discriminant. Now since we know our points being 0, 1, and 0, negative 1, we could see how each of these points fit our discriminant. So at 0, 1, which remember, this means our x is 0, our y is 1, our discriminant equaling 12y becomes 12 because we're plugging in 1 to our y. And at the point 0, negative 1, our discriminant at 12y equals negative 12, since we're plugging our y as negative 1. Now again, remember, this is our discriminant at this certain point, and this as well. And we can check back that our double derivative of x, which is over here, is 2, which is a positive number. So that means our double derivative of x is greater than 0. Our discriminant over here is a positive number, so that shows that our discriminant is greater than 0, meeting the requirements for a local minimum. Now over here, we don't even have to look at our double derivative of x because, look over here, our discriminant is a negative number. And going back to our rules over here, if our discriminant is less than 0, this gives us a saddle point. So this eventually rules out to be our saddle point. So our conclusion could be the point 0, 1 is a local minimum, and the point 0, negative 1 is a saddle point. And there you go. That is our final answer. Thank you guys for watching, and good luck on your exam. Oops.